Слышно? Один, два, три. Так. Раз, раз. Ну, смотря как говорить будет. Ну так. Так нормально? Да. Давай что я. Один, два, три. Один, два, три. Один, два, три.
Горячев.
Добрый день. Это уже 5-я по счету конференция, которую мы начинали 5 лет назад. Людмила Константиновна у нас здесь где-то, я ее не вижу. Вот наша главная героиня сумела поддержать темп таким, что это 5-я по счету. И ее брат Игорь Ужинский, наш бессменный модератор, пленарный и помощник в формировании международной программы. А также я хочу поприветствовать всех участников, которые сегодня нашли время для того, чтобы приехать и пообсуждать с нами основную тематику этой конференции. Я бы коротко хотел сказать о тех приоритетах, которые сегодня сформулированы физтехом на ближайшие 5 лет, как стратегическая программа развития, которая 22 ноября будет заслушана на наблюдательном совете МФТИ, которое будет проходить, это будет выездное заседание наблюдательного совета, будет проходить на базе правительства Московской области под председательством губернатора Воробьева, поскольку он является членом нашего совета, и, соответственно, председателя НАП-совета Суркова Владислава Юрьевича, который продолжает активно работать. Если говорить о прикладных направлениях, стратегически важных для физтеха, то их выделено 3. 3 прикладных и 3 таких фундаментальных направления исследований. По прикладным, первое – это программа арктической технологии, это Арктика. И в рамках арктической программы самым крупным и самым первым финансируемым проектом по линии Минобороны является проект, связанный с созданием спутниковой системы высокоскоростного доступа к наземным информационным сетям для труднодоступных регионов на базе спутниковых группировок «Благовест», в первую очередь, это военный спутник, «Экспресс», «Ямал», дальше «Меридиан», «Сфера», высокоэвлиптическая сфера, это не та сфера, о которой сейчас много говорят. Финансирование по этой программе открыто, оно очень крупное, это 804 миллиона. Мы должны экспериментальные образцы вывести для испытаний и исследований в 2020 году. Это центральная земная станция, раз, это спутниковые терминалы, 2, это модемы, это передатчики до 44 ГГц, то есть это очень серьезная работа. И здесь вместе с нами радиофизика, компания радиофизика, и информационная система, спутниковая система имени Решетнева, и ряд других очень важных для нас партнеров. Это первая, самая, важная позиция в арктической программе. Второе стратегическое направление – технологии искусственного интеллекта. По технологиям искусственного интеллекта у нас 7 направлений. Мы выиграли очень крупный грант в всероссийском конкурсе на создание центра. Это на сегодняшний день 600 миллионов на 1 год, по существу, плюс там последующее финансирование. Я не буду там останавливаться на этой программе, но там тоже очень важными направлениями являются средства телекоммуникаций. Если мы говорим о телекоммуникациях. Но там акцент делается уже не на высокоскоростной доступ и не на широкополосные системы, то есть там акцент делается на телеметрию, то есть узкополосные системы беспроводной связи, передачи данных. так называемый LP1, это для интернет-вещей, и вот управление оборудованием. И третья приоритетная программа в нашей стратегии – это космос. И речь идет не о ракетах, там, полетах, а речь идет об использовании космического пространства в интересах связи, навигации – раз. Второе – дистанционное зондирование Земли – два. И третье – метеорология. Опять же, с акцентом на связь и навигацию. И тут опять мы вот возвращаемся к телекоммуникационной тематике вот в этом направлении. Поэтому тематика, которая охватывает наша международная конференция, я это называю инжиниринг и телекоммуникации, вот она сегодня среди первых приоритетов в исследованиях и разработок на физтехе. Поэтому очень важно, чтобы вот эта конференция у нас продолжала вот традиции и была вот площадкой, хорошей площадкой для обмена мнениями, решениями, предложениями и так далее. Я думаю, что через год мы сможем здесь обсудить первые результаты работ вот по этим уже новым стратегически важным для нас направлениям. А то, что сегодня будет круглый стол по спутниковым связи, вот у нас наш хороший партнер здесь, организатор арпилогов присутствует, ему тоже благодарны за то, что вот такой круглый стол помогает нам организовать вместе с радиофизикой. Ну, всем желаю успешной работы. Еще раз благодарю вас за то, что принимаете участие вот в этой конференции. Спасибо.
Thank you very much for your kind words. And I also want to say a couple of words concerning our conference. Excuse me for my poor English. I have very small practice. So, as Sergei Nikolaevich said, it's fifth conference, and we try to not to preserve the level of this conference, but try to make high level for our conference. We have new 3 traditional sections this year and 1 new section, a new direction for discussions, artificial intelligence, as also Sergei Nikolaevich says, it's one of the strategic directions of developments in our university. And I think this direction is very interesting and for many participants. And we will have a very interesting and strong round table on satellite communications. All our meetings and sections will be casted in internet, and many people have a chance to hear it, and we'll try next times to include also participation, not direct but distant participation in our conference. I think that we have very interesting reports on our plenary meeting. Our key speakers prepares very, I think, very interesting teams. So I don't want to spell your time more, and I'll propose to begin our conference. Thank you.
Hello, my name is Igor Yuzhinsky. I'm kind of traditional moderator for this plenary session, and we will start our plenary session right now. Because of some unexpected situation, we have a change in our program, and our first speaker is Professor Jin Minglu. His report is titled Spectrum Sensing Techniques for Cognitive Radio. Professor Jin Minglu, he works for Dalian University of Technology in China. He graduated from his master's degree in Communication Information Systems from Beiyang University in China. He has a very distinguished career. So he spent significant time in Korea supporting development, and so just in Korea. And so he has a lot of awards and recognition from both Chinese government and scientific societies. He is an expert of National Natural Science Foundation of China and expert at National Science and Technology Progress award, member of this committee as well. So we are looking forward to your presentation, Professor Jin Minglu, and so let's also go forward with this presentation. Thank you. Yeah,
thank you, Professor. First of all, I say something because my English also very poor, also Russia, but I'm trying my best to give my presentations. Dr. Saki Garichivu, thank you for your kind invitation, and Dr. Alexander Dorgoichiv for your kind welcome speech, and thank you, Igor Yuzhinsky, for your kind introduction. And ladies and gentlemen, good morning. I'm very honored to give this speech with the topic on special spectrum sensing technology for cognitive radio networks. Next. My talk have 4 parts. First is the introduction of cognitive radio toward 5G, and the second part is a review on classic spectrum sensing techniques. Third part is some work have done in our lab on special spectrum sensing techniques, and at last, some recent research issue and the conclusion summarized. In introduction part, I will first review 5G technical scenarios and the challenges, and the current spectrum utilizations. The demand of growing communications contradict the limited spectrum resource. So now it's calling for full spectrum area towards 5G, and the cognitive radio technology is one efficient solution for this contradiction. So in this cognitive radio technology, the spectrum sensing is first important for cognitive radio technology applications, And then I briefly review some spectrum sharing and practical challenges for spectrum sensing. Yeah, this shows the 5G technical scenarios and the challenges. With the rapid growing market of wireless broadband and high data rates, the fifth generations envisions maybe 1,000 times increased capacity and 10 to 100 times data rates and 10 to 100 times connected device compared to the 4G wireless networks. So for this purpose, there are some key technologies as massive MIMO, ultra-dense network, novel multiple access, and all spectrum access. This morning, I'm going to talk mainly on spectrum sensing from all spectrum access point of view. This shows the current spectrum utilizations. You know, the totally today's wireless networks are regulated by a fixed spectrum assignment policy, and the spectrum used is very underutilized. So there are need all spectrum access. And the spectrum, you know, already fragmentation, and we used the fixed allocation policy. Sorry. Next slide, please. Please, next slide. Okay. So it's coming full spectrum area. And the way to solve this problem, there are two ways. One is new spectrum explorations. One is dynamic spectrum accesses. The spectrum usage in 5G is expanded further from this area to maybe 100 gigahertz or whole millimeter wave. Also is maybe include the visual light communications. And by dynamic spectrum accesses, we use the high, low, or paired, unpaired, licensed, unlicensed, and the contiguous and the non-contiguous bands dynamically use it. And the key issue for this is channel measurement. Channel measurement is a key issue for this use, and the unified access for low and high frequencies. So we talk about cognitive radio. Cognitive radio first proposed by Dr. Mitola, and it's generally defined as a sharply configurable software-defined radio data can change its transmitter parameters, frequency, modulation, data rate, or other, based on the environmental conditions in which it operates. And the cognitive radio have a cognitive cycle, and it's composed of 4 functional components. First is spectrum sensing. It's used to detect the spectrum whole, not use the spectrum. And this is spectrum decision is select the best available spectrum opportunities. And this is spectrum sharing. This is using the selected band to transmit information. And this is spectrum mobility. This enable the secondary user immediately leave the band if the primary user reactive in this state. So the whole spectrum user is like this. This time user jump or like this. So the cognitive radio can be, we think of SDR, software-defined radio, and sense, learn, adapt, and use. Now, I speak to spectrum sharing. Spectrum sharing, how to use the spectrum. There are 3 modes to use the spectrum. First is interview spectrum sharing, and the second is underlay spectrum sharing, and the third is overlay spectrum sharing. This is the first case. This 2 is underlay overlay case, as this figure shows. In the interview spectrum sharing, the cognitive radio should periodically detect the existence of the primary user of the band, and then utilize the band if it is idle. And in underlay spectrum sharing, the cognitive radio are allowed to operate if the interference caused to primary users is below particular transmission power threshold. And in overlay spectrum sharing, the cognitive radio should be able to decode the primary user's message and encode its message so that the interference can be avoided. So they have some factors in practical challenge for spectrum sensing. The first factor is, the required SNR is maybe very low. It may be well below minus 20 dB. The second is multifast fading, and the time dispersions of the white channels. It's complicated the sensing problem. The third is noise and interference level may be fluctuate, is changing with the time and the location. This is which yields the so-called noise power uncertainty issue for detection. Okay, the second part I will review on existing spectrum sensing techniques. And in this part, I first introduce the spectrum sensing formulation, then review some existing spectrum sensing algorithm. They give the conventional 2-stage implementation, and the last, the special spectrum sensing access scenarios. Spectrum sensing is nothing. It's a very classical signal detection problem, or it's very binary hypothesis testing. The primary user have 2 states, active or silent. In active state, the signal from primary user, it may be propagate multipass channel and mixed it with noise or interference at the receiver. In the silent state, there are only noise or interference. So the spectrum sensing is to make a decision on the binary hypothesis testing. What's the optimum? By Newman-Pearson theorem, you know, the optimum of spectrum sensing is to achieve the highest detection probability for giving false alarm with a fixed number of samples. This is a little similar to radar signal detection. Okay. We know that generally this kind of detection problem or hypothesis testing, the most optimum is likelihood ratio test or generalized likelihood ratio test like this. This is optimum. But the major difficulty for this, in using this, we require of the exact distribution. In practice, it's very difficult, very difficult. So, to implement this kind of detection, there are three kind of methods. The first is requiring both source and signal and noise information. That meaning they need all information, signal and environment noise or interference. The typical example is matched field. And this is optimal and fast to achieve high precision gain and sometimes require for synchronizations. The second one, we call it semi-blind detection. This is only require noise power information. The typical example is energy detection. And this is very simple. And sometimes, if the source signal is ID distributions, this is also optimal. But for this detection, have some problem. First is have SNR words. That meaning, at the very slow SNR, the performance is very bad. Second is the non-robust to noise power uncertainty. Because in this we need correct noise power information. The last one is blind. We call it is blind detection method. And in this, we know information on signal, source signal, and the noise power. The typical example is maximum to minimum eigenvalue detection method. It's like this. This is a sample covariance matrix of received signal. And generally, the conventional spectrum sensing is focused in time or frequency or geolocation demands. But there are other dimensions we consider. For example, we can think of code, waveform, or its angle information. So now I introduce this from spatial dimension, we consider the spectrum sensing. Now, this shows the conventional two-stage implementations. Generally, we first perform the detection processes in this stage. And you can use many kind of detection method. Then we need another position stage. In spatial, we need to estimate the AOA, the arrival of angle, and you can use as many algorithms. Then, if we detect the H0 hypothesis, then you access any directly, as like this. If this one you have detected, we can communicate avoiding PU communication direction. That means we have detected, then we can communicate this way. So the conventional method is in detection and the position is have independently. So it's make some this two stage is a more complex process. So we think why not the detection and the position fusion? We combine it together. The answer is a spatial spectrum. Spatial spectrum is also called the Peugeot spectrum, as a function that gives an indication of the angles of arrival based upon maximum worth angle. And this example. This is hypothesis test 0 is hypothesis 1, like this. by using spectrum, we have some advantages. First is high detection performance. We can exploit the inherent feature of spatial spectrum. Second, can reduction of the complexity of spectral spectrum sensing. Because by using spatial spectrum, we combined the two strategies in one. And at last, it's improving capacity of CR networks because we can access in spatial angle dimension. Oh, it's time for part 3. This is some work I have done in our lab, and I shall introduce AOA estimated-based detection. We have 2 algorithms proposed. One is the eigenvalue-based spectral sensing algorithm. Then we discussed the spatial temporal resolution trade-off issue. This is the system module as like this. We assumed the linearly uniform antenna array, and this is the primary user signal is entered in these directions, and we're using by vector to combine the received signal. We get the received signal as like this, and we can use the Bartlett AOA estimation algorithm, and we can get as like this in one direction. If we select the vector as like this, that means steering vector of the vector, then we can get as like this spatial spectrum. And then we can see in 2 hypotheses, there are very different kind of spectrum as like this. This is no signal. This is a signal coming from this direction. So we can use the spatial values of spatial spectrum can differentiate the 2 hypothesis tests. So we proposed 2 algorithms. One is maximum minimum delay sum ratio test. Second is average minimum delay sum ratio test. It's a similar maximum minimum eigenvalue test and the energy to minimum eigenvalue test. And this gives us some simulation results, and you can find more detailed information for this journal. We have published in this journal. Okay, and from this simulation, our proposed algorithm is better MME or EME, the already known algorithm. The second feature we noted is the spatial spectrum have a very interesting property that is central symmetry feature of noise spectrum. We already see the spectrum at H0 have like this, and at hypothesis 1 have like this, and we noted in this study they have a very strong symmetry as like this. So we used the Eurasian distance to calculate the symmetry of spatial spectrum and to perform the detection process. And we also get this kind of simulation results. Also, our algorithm have a better performance than the existing algorithms. You also can find the more detail in this paper. We have published attribute chain caching or Victor technology. Sorry. Okay. So far, we have considered special correlations of the incoming signal, but the signal also correlated in time dimension. So now you maybe noticed the very hot topic in signal processing is spatial temporal signal processing. So the retrieved signal, before we consider space correlation, now we consider the time correlations. And this shows, this is retrieved covariance matrix. This is the noise correlation matrix. This is the signal correlation matrix. This is the channel matrix. And this is the corresponding eigenvalue. So our algorithm, the existing eigenvalue-based algorithm is not a full take advantage of all eigenvalues. It's concentrated the maximum or minimum. So we think, how about to use all of the eigenvalue? So we begin with the covariance, the sample of covariance matrix. Then we can find the eigenvalue. And the eigenvalue distribution is very complex. And we used the random matrix theory. Because of this is without the matrix, we can find the eigenvalue distribution. So we can get the ART is like this. So we get the optimum eigenvalue weighting detection algorithm is like this. Then we also get the semi-blind optimum eigenvalue weighting detection is like this. And blind eigenvalue value weighting detection algorithm. More detailed information you can find in this attribute chain wise communication. This also shows the simulation results, and it shows with the prior informations, our proposed OEW performs the best. If we, with noise variance only, this is a semi-blind detection, our proposed algorithm performs better than existing other algorithms. If without any information, this is a blind detection method, our proposed BEW performs better than already known MME and AGM. Now, I speak to spatial temporal uncertainty principle. Because we use the antenna array, it's scan the space, and we can get this kind of beamforming. And every beamforming, you need some time to calculate. Suppose this time is tau 0 and tau 0. Then we find in this application, we want to achieve high spatial resolution and high time resolution. This means sensing time. But we find that this delta t and this delta theta, this is angular resolution, this is time resolution. The multiplication must more than 2 pi tau 0. We call it is uncertainty principle. So when we design the Mac design, we must consider this principle. And in terms of this principle, we have proposed the optimum make design algorithm, and this algorithm can be described as like this. This means spatial multiplexing. This means exact time proportion. And at last, we can describe in the optimizing problem. And we get this is a spatial resolutions, and it's throughput. So we can see there are one angle resolution. It's resulted in the best higher throughput performance. And this is total frame durations, and it's throughput. And for given angle resolutions, there also is increased with the time, the total frame durations. And more detail you can find in this paper. Okay, part 4, I discuss some recent research issue. And in this part, I discuss is for duplex spectrum sensing, and the spectrum sensing, from spectrum sensing to spectrum inference, and big data or deep learning based deep sensing issue. Yeah. For duplex communication, before people have not considered many, but now have considered or have now it's feasible to use it. So the for duplex communication technology also is a candidate 5G technology. And for this communication, the most concerned problem is self-interference, self-interference. But now there are many methods to cancel the self-interference. This figure shows is half duplex process. This is for duplex sensing problem. And the difference in the full duplex sensing, the detector or the sensing all time, but in half duplex is sensing discrete mode. So the main benefits of FD in spectrum sensing is can concurrent sensing and transmitting, and the concurrent transmitting and the receiving. And it also improve the sensing efficiency and the secondary throughput. Also, it can be mitigation of the hidden terminal problem. And this table is summarized between edge-based sensing and the FD-based sensing issue. Because the limit of time, I skip this. You can find in the literature. So this shows the full duplex spectrum sensing formulations. The signal module is like this. And you can find out the only difference is self-interference signal is registered. And this shows two scenarios. Is interview CR scenarios, is underlay CR scenarios with FD CR nodes. And for this, there are some enabling technology to use the full duplex spectrum sensing. First is self-interference mitigation schemes, and the waveform-based sensing, and the multiple antenna signal processing, and the power control. Because this is all time is sensing, so the power is a very concerned factor. So for research issue or future direction, is FD-based concurrent sensing and transmission, or FD-based concurrent transmission and reception, and the self-interference cancellation and the related issues. Also, is energy efficiency is very important. Okay, yeah. Okay, next is now is from spectrum sensing to spectrum inference. conventional speaking sensing just use the is present signal, but we can use the geolocation speaking database or radio environment maps can enhance the speaking sensing. So now the speaking sensing is become from sensing to inference. From sensing to inference. This shows spectrum inference for spectrum sharing in 5G. So with the spectrum inference, can reduce the sensing time and the energy consumption and to improve the detection performance of spectrum access point. And this is the last issue. This is the big data and deep learning based deep sensing. You know, the radio signal is, we can think is big data, and we can use it to do the speech sensing. And more important, we can use the deep learning to do. So it becomes from single dimension to multi-dimension. So we can find out the deep information of primary user. Then we can to do the feature classification and the behavior prediction. Okay. To sum up, you know now the information and the communication technology converging. Also, various information service and the cognitive radio is converging. You maybe we share information a finger away, everything in touch. So the speaking sensing is now in its cognitive or in its cognition stage, and they have a feature like this. Sensing dimension is from low to transfer to high. We call it is deep sensing. And the sensing mode, before it's passive, now it's active. It might be cooperation or the coordination. And the sensing issue, before we concerned merely noise. Now noise not a problem. More important, the interference, also with the low SNR. That's all. Thank you for your listening.
So we're really just a bit behind of schedule, but still, if you have some burning questions right away, please go ahead. Do you have one question which we must answer right away? Otherwise, you know, thank you very much. I think that, you know, this utilization of spectrum and all the things what you just presented is extremely important, not only for radio, you know, but for other use of wireless, or all the wireless things, I mean, really related to spectrum efficiency and cross-utilization, what you just presented. Thank you very much.
Thank you.
Yeah. Okay.
Thank you.
Thank you. Now we invite for presentation Professor Chang Hyun Kyu. Professor Chang, he arrived from Korea. You know that Korea is a kind of leader, the world leader into so this kind of things, you know, just everybody knows just Samsung and KAIST. And Professor Chang had a really very distinguished career in, you know, multiple multiple places which are world leaders in these areas. And he spent quite a time in the United States. He worked in he worked in the United States for SK Telecom in New Jersey. He defended his PhD in New York University. Really, just it was Long Island, so just Long Island University, Polytechnical University, one of the best technical schools in the United States. So in Brooklyn, New York. He is the author of about 20 journal papers and 44 international conference papers, and we are looking forward to your presentation.
Thank you, Professor Ujinsky. Thanks for your
nice introduction and invitation. Actually, it is my pleasure and a great honor to be here as a speaker. And my presentation is a little bit different from the previous speaker. Actually, I have the theoretical result. Actually, I prepare my material in some intuitive, practical presentation. This is point. Okay. Actually, my topic is the mobile wireless backhaul, which is using the millimeter wave 20 around the 28 gigahertz, and it is. I believe that this is one of the technology for the 5G and 5G beyond. It's not work. Which one? This is right? Which one is the down? Okay. This is down. Okay. Actually, my presentation is two parts. One is the first part is the 5G introduction, short brief of the 5G introduction. And the second part is I want to give some introduction of the mobile axial network. Actually, this is the research and development outcome achieved by the ETRI. Actually, I'm working for ETRI. ETRI is the research institute in Korea, and almost all fund is funded from the government. Okay, so the mobile axial network, I will give some introduction about that with the proof of concept, and it is just in front of the commercialization for the Seoul Metro line. Okay, I will give that. Okay, let me start some the history of the mobile communication. As you know, I think some of the audience is very familiar with the 1980s, the first generations communication. Actually, this is analog. The analog is the first commercially produced in 1984, and that time this is we call it is the brick phone. Actually, the size and the weight is very heavy and like a brick, and the retail price is very, very high. In Korea, in 1984, the car phone, the price of the car phone or cell phone is almost the same the price of the automobile, almost the same prices. The EMS and En&T and the text is the communication methodology. I think that some of you is very familiar with this. And the second one is the second generation. It's over the 1990. It's the digital AMS and the GSM, GPRS, and the CDMA technology was introduced for second generations. And early of the 1990s, and that time, firstly, digital voice coding and the modulation was used. And the light, very, very, the light and cheap. That is the second generation characteristic. So the first and second generations, actually, the major characteristic is from the analog to digital. Digital means the digital provides the upgrading the capacity and the voice qualities. Okay. The third generation is the wideband CDMA in Europe, and the CDMA 2000 in North America, TDS CDMA in China, I guess the WiMAX in Korea, and this kind of very different methodology was used. And the typical characteristic of third generation is the over the year of the 2000 is that at the time, firstly the mobile phone make people connect to internet. That is very special feature about that. This is the third generation, and the late of the this year, the iPhone makes people crazy, and all the applications downloaded in the mobile phone, and some new ecosystem was introduced. This is the third generation, and right now, actually, this is the fourth generation. It's after the year of 2010, and the LTE advanced and the WiMAX enhanced. This is some methodologies and the standard for communication. But right now, the WiMAX is in the market and the field. I guess only the LTE and the wideband CDMA up version is currently available in the first generation. One of the major characteristics is the global mobility support. Before the fourth generations, you need to, actually in my case, if I have some business trip to America, then I needed to exchange the mobile phone to other mobile phone that can be available in United States. That means the frequency band in some region is different for communication. But in the first generation, the ITU, International Telecommunication Union, trying to harmonize the frequency band for mobile communication. Actually, that is the first. Okay. The next slide is the brief history of mobile service, especially in Korea. But actually, the milestone and time schedule is almost similar to the world. 1984, the AMS we start, and 96 the CDMA, and the third generation HSDPA, the wideband CDMA, and in the fourth generation, almost 80% of the Korean people using the LTE, and the LTE firstly introduced in the year of 2011. But after that, LTE advanced. After 2 years of the first introduction, we provide some LTE advanced, 2013, and now LTE advanced still. But one of the features is that even though the same name of the LTE, but the maximum data speed is different. Actually, right now is maximum 700 megabps can be provided by the LTE. And 2020, actually, the 5G, the standard will be finished in the year of the 2020. This is the regular and the official milestone for 5G by the ITU. Okay? And one other characteristic is the mobile communication. The major trend is to trying to upgrade the data speed from the voice kilobps, megabps. At this time, almost up to 700 megabps. But in the 5G, the maximum data rate will be 20 gigabps in the year of the 20. Okay. So what's the difference between before 5G and after and the 5G itself? As I mentioned before, before the 5G and until the 4G, the major trend is the upgrading the data speed between the mobile station and the base station. But in the 5G, there are two other different characteristics expected. The big pipe is the broadband. This is the conventional approach. But the other two is the low latency and the massive connectivity is the totally different characteristic of a mobile communication. I think these two characteristics may provide some new market. That means the new ecosystem for money. Actually, so for example, for this kind of low latency, that very connected with the V2X. That means the vehicle-to-vehicle communications. And massive connectivity can be applied to the smart city and the smart factory. Actually, this is the picture of the Siemens in the some Germany area. I think you cannot see there any people, and because the IoT device was installed there, and they are communicating with the base station in time and on time. That means the 5G, another capability of the 5G. Okay. Officially, the 5G capability defined by the ITU, International Telecommunication Union, and the official name is the IMT 2020. And before, in case of 4G, IMT Advanced is the ITU official name of the 4G, but in the 5G cases, IMT 2020 is the official name. And there are lots of the capability defined, like peak data rate, and the user experience data rate, and the mobility support, and the latency, and the connection density. And actually, right now, regarding the 5G, all the 13 different kind of the capability was defined. Among that, the major capability like this, compared to the 4G LTE, regarding the data rate, is there 20 times then more than 4G. It's up to the 20 gigabps. And the latency, this latency defined by the time delay between the one-way delay between the mobile station and the base station. It was a 10 millisecond in the 4G area, but in 5G it's the 1 millisecond. Connectivity is the device, number of device per square kilometers. But in the 4G cases, 10 to the 5, but in the 5G cases, 1 million device can be connected within the kilometer by kilometer, square kilometer area. That means if you break down that 1 meter by 1 meter, the 5G can allow the device, communication device. This is the little bit different thing. Okay. Why 5G? Actually, I explained the 3 different kinds of 5G characteristics. Enhanced mobile broadband. Actually, that is the conventional approach. And the other one is the low latency, and the other one is the massive connectivity. Each one generates new market. For example, in the enhanced mobile broadband, since it provides a high data rate, 4K or 8K UHD can be enjoyed in the mobile phone. Even the hologram can be enjoyed in mobile phone. I think some of the manufacturing vendor like Samsung and the other big vendor Huawei, I think they are preparing some very killer application for mobile station for 5G. That is one of the candidates is the hologram. The VR and the AR and the mixed reality also is the new market generator. And regarding the low latency and the tactile internet is possible. What is the tactile internet? Actually, regarding the LTE communications, one end-to-end delay is covered up to the 40 to 80 millisecond. So that means we cannot use that LTE in the real time critical application like machine control and some remote operation. That kind of application LTE cannot use to that kind of applications. Still, the connected car is a very hot issue right now. Why in the LTE generation we cannot use the, why the people did not use the LTE technology, the connected car. That is that LTE cannot guarantee the time response in time and on time for tactile internet. But in the 5G cases, I guess the connected car, the V2X, vehicle to vehicle, vehicle to infra network, vehicle to anything. Okay, that can be the possible. Okay, the third one is massive internet, massive IoT. There are lots of the IoT devices in right now, but the remote control can be achieved by this characteristic. But the difference between the LTE and the 5G regarding the massive internet, two things. One is the 5G provide very ultra high reliabilities, like in time and on time. And the other thing is the number of connections, So 1 million device can be deployed. Oh, sorry. What this is? Okay. Okay, there are so many 5G technologies we now think. Actually, we can identify the three different groups. One is the spectral, upgrading the spectral efficiency. The other one is the new spectrum development, and the third one is densification. First, regarding the spectral efficiency, the massive MIMO, there are lots of antenna can be used in the mobile station and base station. And the other thing is the flexible link carrier can be used. For the densifications, multi-connectivity is the new feature of the 5G. That means we can use the very small cell or overrated cell. That means here, some small cell base station can cover the small cell, but in the macro cell, the other base station can cover also to me. So if I need some very fast download, then I can use the very small cell. But if I need some slow and just such kind of traffic, then I can use the macro cell. That means the overlay cell. This kind of technology also one of the candidate technology for the densification. The spectrum issue is very prominent, very promising adoption of the 5G. That means the millimeter wave can be applied for access technology, not the backhaul. That is the one prominent technologies. Okay, so regarding the millimeter wave for 5G, actually, world WRC is the ITU recommendation, such kind of recommendation for harmonizing the frequency, and they defined the candidate frequency in the millimeter wave band for 5G. This is the specific band for 5G in the world. Okay, so regarding the millimeter wave in the United States in the late of 1990, the RMDS technology was adopted the millimeter wave for the access the last mile, but that time the CMOS technology, they have the CMOS technology limitation, and the propagation range is the limitation for high frequency. So, but right now the CMOS technology improved, and the short range, actually it is the demerit of the RMDS era. But right now the short range is very adequate for small cell. Well, that's the merit. Okay, so that's the reason why the millimeter wave can be allowed or feasible for access and backward link. Okay, that is the second part of the thing, the mobile XO network. Actually, this is the problem statement like this. How to connect people. Actually, the left time is it's good. 5, how about 3 minutes? Oh, okay. Oh, very tough. I'm sorry about that. Okay. In Korea, there are lots of people gathered in the Seoul City Hall. Left is the City Hall, the right is the candle demonstration. Actually, it is to people gathering to impeach the president, actually. That time, the 400 base station was deployed in advance. Only 5 mobile base stations. But that gathering is expected. But if the people is gathered unexpected, then how can deploy the network? That is the problem. Okay, that is what. Not only the urban hotspot services. If some hotspot is moving, like a train, subway, and a bus, or drone, well, this kind of a base station is moving, then how to connect network? That means the how to base station connected to core network. That is that will be the problem. So traditionally, the backhaul is the interface between the base station and the core network. And depending on the function split within the base station, then actually the core network, the interface name is the backhaul, and the other 2 types of the backhaul is the frontal and the middle, depending on the function split between within the base station. But this kind of a base station, this kind of base station is moving. Then how to connect this kind of base station to core network? That is the first problem setting. So now we introduced in the R&D level, we introduced the mobile XO. The XO is backhaul, middle, and the frontal. Mobile XO network we introduced, and the core network can be by this kind of a moving base station can be connected to the core network through the mobile network. That is our very lovely concept. Okay. So this kind of dense hotspot or the stadium solutions, or as I mentioned, the moving train, such kind of network can be connected through this mobile. Okay, actually I have a two minute video streaming, and you can just pointing that. Okay, just okay. There is no actually the Okay. Okay, around the, it's a little bit echo. So. We need the, okay, good. Actually, final goal is to, within, the people within the train, we would like to provide some high capacity of the wireless access. So within the people can using the social network and the very high resolution online game and other stuff. That is actually the basic goal to for this R&D project. Okay. Thank you. So in order for that, we have some prototype system and using this little bit different the frequency band, and in the actually the last year February we give some trial, the commercial trial in Seoul Metro. Actually, the line is the very the worst environment in Seoul, the subway, because of very there are lots of curve, and within the tunnel the construction is very bad for millimeter wave propagation. Okay, so next slide, please. Okay, so I will give the right 2-minute the video streaming also, the right side. Provide inside the train. Thank you. Okay, this is just some spec, but one of my notice that we used the 25 to 26 gigahertz. Actually, this is not the LTE frequency. This is the FACS, Flexible Access Common Spectrum, defined by Korean government. It's like ISM band. That means the service provider do not need to pay the frequency license fee. Actually, LTE license is very expensive. But in this case, this frequency band is free. So service provider can really providing their wireless access to Seoul people. That's the commitment of the city, the mayor of the Seoul. Okay, that is the, I'm gonna, and the Wi-Fi service, we compare the Vibro backhaul is the 3.85 megabps, but in the LTE backhaul, the 11 megabps, but in this system is 360 megabps supported. So very fast, and I think very, I believe very the promising technology for wireless backhaul. Okay, I will skip that. Okay, actually, in summarize to my talk, the three features of the 5G mobile communication is the three different enhanced mobile broadband, and the second one is the ultra reliable and the low latency communication, and massive connectivity, and the specific metric is suggested by the standard like this. And the millimeter wave is very adequate for. Some people do not agree about the adequate, but I have to say like this. The millimeter wave is very adequate and fit for the small cell and 5G applications. And I suggested the new mobile XL network defined as a wireless transport network connecting mobile RAN and the packet core. Actually, I showed the one example of the typical example of the MXN is the some proof of concept and commercialization demonstration model in Seoul Metro. Okay, thanks for your attention, and that's all my preparation. Thank you.
Okay, thank you very much. As in previous case, we do not have too much time for discussion, but I think that there is some burning question. Yeah, please.
My question was how to deal with the rain, the fading. I guess this is the physical limitation for the millimeter wave. Thank you.
Your question is the fading? Yeah, but okay, I understand it. Millimeter wave in the outdoor is very, very serious challenges. But in this case, is the Seoul Metro line is used the tunnel. So based on the measurement result, the tunnel acts like a wave guide. So that's the reason why we can deploy this kind of technology in the tunnel. But in the outside, I think there is much more the challenge other than the tunnel case.
Okay, thank you for question. Yeah, I think that we will have opportunity to discuss it, later in, just in formal environment and just during dinner and so on. We, of course, well behind our schedule. And now I would like to give our podium to Professor Alexander Zhdanov. I hope that you have opportunity to download the presentation. This presentation is biologically inspired approach to simulation of language effect and human-machine communications. It is Professor Zhdanov is he works for Lebedev Institute of Precision Mechanics and Computer Engineering. Of course, he is a mathematician, and it's really very, I remember when artificial intelligence only kind of emerging, so from the point of view, all kind of discussions, and if it is, there will be some robots or, just, creatures which will really threaten our existence. But what Professor Zhdanov has done in his work and his career is really just, first of all, to understand in depth what is the relationship between human brain, human intelligence, and potential artificial intelligence. And I think that it would be extremely interesting to listen to his presentation. and I'm sure that we will learn a lot. Professor Dezhanov has a distinguished career in academy, and so just in the former Soviet Union in Russia. We welcome. We would like to hear your report. Thank you. Okay. Yeah, Professor Zhdanov wants to speak in Russian, but do you have your slides in English as well? In Russian. Okay. In Russian.
Мне нужно 3 руки, поэтому я, с вашего позволения, сяду, чтобы указкой пользоваться. Добрый день. Извините еще раз, что сидя. Значит, я хочу рассказать о своем некотором таком предлагаемом мною подходе к созданию человеко-машинных интерфейсов на таком немножко аппаратном уровне нейронов. Но поскольку подход оригинальный, мне каждый раз приходится начинать очень издалека, поэтому я так быстро, конспективно про это расскажу. И так. Вперед, назад, никак не хочет. Вперед у нас, да? Так, назад, нет. Сейчас, секунду. Вот так, все. Значит, еще одно замечание. Я очень люблю нейросетевиков. И нейросети, но любовь не может быть безграничной, поэтому я там буду иногда критиковать, не принимайте это близко к сердцу, просто мне приходится как-то аргументировать. Значит, я считаю, что следующим этапом в развитии технологий будет являться, будет являться адаптивность, потому что наука уже очень много дала нашей жизни и технологиям. В 21 веке я считаю, что основное направление будет связано с развитием адаптивных машин. Почему? Потому что в природе, как мы видим, все чудеса управления, которые демонстрируют природные системы, они связаны с адаптивностью. Все системы адаптируются, и те чудеса, которые они проявляют, это результат их свойства адаптивности. Нам приходится, или не приходится, придется идти этим же путем, и этот путь очень разительно отличается от того, что мы видим сейчас. Сейчас у нас машины оптимизируются на этапе конструирования, на этапе проектирования, они в своем лучшем виде сходят с конвейера. А дальше начинается уже только старение, и никаких следов адаптации в течение жизни мы не видим, и это неправильно. Значит, почему дело обстоит таким образом? Потому что, главное, это отсутствуют эффективные методы самообучения. Есть еще и другие причины, нет специалистов, нет технологий, нет спроса, в конце концов, хотя в последние годы он уже появляется. Скоро будут люди спрашивать адаптивные телевизоры, адаптивные холодильники, пока еще редко спрашивают. Значит, сейчас все методы, которые используются для построения систем управления, они, как правило, проблему адаптивности решают очень косвенно, очень косвенно. Основные методы я здесь перечислил. Можно сказать, что с адаптивными подходами здесь довольно напряженно. Но я сейчас объясню, почему на примере нейросетей. Еще раз повторяю, что я их очень люблю, но тем не менее у меня к ним большие претензии. Значит, эта ситуация, когда известно, что нейросеть – это некоторая модель мозга, нервной системы. Представляем себе, мозг с таким количеством синапсов 10 в 15 степени, да? И для того, чтобы настроить нейросеть, нужен некий таинственный, учитель, который имеет какую-то странную обучающую выборку, видит одновременно, что там было подано, я даже не знаю, какие тут цифры нарисовать, но это количество входов, наблюдает, что там было на этом жутком количестве выходов, имеет в уме некое представление о том, что там должно быть, и находит разницу между выходом и входом, и начинает каким-то таинственным образом залезать внутрь мозга и все эти 10-15 степени синусов настраивать. Совершенно фантастическая ситуация, с скорее всего, ничего общего не имеющего с природой. Значит, почему дело обстоит таким образом? Потому что вот тот элемент, на базе которого строятся нейросети, это пороговый сумматор, в нем нет ни малейших следов адаптивности. Да? То есть он требует некоторого внешнего учителя, который вот почему-то будет ручками настраивать эти веса независимо от нейрона. Ну, я считаю, что это неправильно, потому что в нейроне, в принципе, значит, все должно быть адаптивно. Ну и еще раз, вот на базе таких пороговых сумматоров, если мы хотим построить какую-то значит, распознающую систему, то нам приходится, естественно, вот, значит, настраивать эти гиперплоскости в признаковом пространстве у всей этой системы целиком, а это можно делать, ну, вот, естественно, только по обучающей выборке с помощью учителя, и никаких других вариантов я тут не вижу. Все это проистекает от того простого момента, что отдельный элемент, он не самообучаемый. Поэтому, значит, вот где-то лет 30 назад, или там 25 минимум, да, вот была предложена такая модель нейрона, и я глубоко убежден, что нейрон биологически это небольшая самообучаемая система распознавания. Нейрон этот описан, формализован, каждый раз приходится объяснять, что это не тот нейрон, неформальный, вот он так-то и так-то. Короче говоря, я его так скромно назвал нейроном Жданова, и если интересно, то как бы формализм есть, чтобы мне не объяснять долго, о чем идет речь. Ну вот так вот, значит, можно пользоваться этим названием наряду с нейронами, значит, Хопфилда и так далее. Да? Может быть, звучит не так красиво, но тем не менее. Значит, в чем смысл? Смысл состоит в следующем. Вот я считаю, что нейрон – это самообучаемая система распознавания. Значит, для того, чтобы он самообучался, нужны правила описания образов. Да? Ну, те, кто знают теорию распознавания, они понимают, что в самообучаемых системах распознавания надо задать правила формирования образов. Значит, это правило состоит из двух частей. Значит, первый вот критерий – это критерий, я его называю структурным, то есть он описывает вот требования к конфигурации входных сигналов, как по пространству, так и по времени. Здесь этот критерий может быть простым, может быть сложным. Значит, кто что здесь придумает? Природа придумала довольно хитрые, значит, критерии вот для формирования образов. Второй критерий – это статистический. То есть нейрон имеет возможность понять, вот эта комбинация, какая из наблюдаемых им комбинаций не случайно, а повторяется статистически. Для этого не нужен никакой учитель, у нейрона все внутри для этого есть. Он просто может подсчитывать, сколько раз встречается та или другая комбинация из тех, которые он может распознать в этом критерии. И вот если оба критерия выполняются, то есть такая комбинация пространственно-временная сигналов, которая удовлетворяет вот этим заложенным, значит, критериям, каким-то пороговым вещам, то этот нейрон обучается. И с этого момента он становится обученным. Он начинает распознавать входной сигнал и выдавать его на выход. Ну вот схема этого нейрона. Значит, вот этот хитрый блок, в котором проверяются пространственно-временные критерии. Здесь статистические критерии. Можно синапсы выращивать по отдельности, можно все вместе. Это уже зависит вот от варианта сложности этого нейрона. То есть нейрон, как самообучаемая система распознавания, имеет несколько фаз в своей жизни. Вначале он глупый, необученный, ничего не распознает. Постепенно накапливает статистику, еще не накопил. Потом накопил, становится обученным. С этого момента он работает уже что-то напоминающее вот этот самый пороговый сумматор, но очень отдаленно. То есть это его какая-то финальная часть жизни, я бы сказал, быть пороговым сумматором. А до этого он должен самообучаться. Вот. И, значит, смысл нейрона вот во входном потоке векторов бинарных научиться распознавать повторяющиеся пространственно-временные комбинации. Значит, вся эта формалистика, она описана. Вот есть такая книжка, может быть, кто-то видел, «Автономный искусственный интеллект», там вся эта кухня, значит, прописана. Мне просто некогда здесь пояснять, я остановлюсь. Есть разные варианты этого нейрона, там, с учетом синаптических задержек различных, там, с внешним импульсом, включающим, моделирующим возвратную коллатераль, либо без нее. То есть есть разные варианты. Соответственно, можно образы разной природы как бы обучаться распознавать какие-то пространственные, пространственно-временные и так далее. образы. Ну, просто буквально два слова. Вы мне скажете, когда? Да, подходит. Значит, вот различные эффекты типа нейрон Дженнифер Энистон, все это у нас давно, значит, реализуется. Я пропущу эти моменты и подойду к механизмам, которые будут отвечать за возникновение языка. Вот, кстати, переходный модуль, что один вот наш нейрон с помощью нейросетей моделируется с помощью вот такой шестислойной небольшой нейросети. Значит, переходим теперь к вопросу, вот, связанному с языком. Значит, дело в том, что в статистическом критерии пространственно-временном, конечно, есть средства помехозащищенности у природных нейронов. То есть, если сигнал распознается много раз, то требования к его полноте снижаются. Вот можно нарисовать как бы требования к полноте входного сигнала. Отсюда следует, что начиная с некоторого момента нейрон может распознавать этот образ при наличии помех, либо при отсутствии некоторых его составляющих частей. Это приводит к возникновению, значит, например, ассоциативных образов, в том числе к возникновению ассоциаций с языковыми идентификаторами. То есть буквально, значит, если мы будем подавать на вход некоторые комбинации структуры нейронов, значит, информацию о реальном объекте и информацию какого-то виде идентификатора, например, звукового, то найдется нейрон, который ассоциирует эти два образа и через какое-то время после снижения порога начнет распознавать этот объект либо при его демонстрации, либо только при демонстрации вот этого языкового идентификатора. И мы можем у себя в базе знаний вызвать, скажем, образ солнца темной ночью, просто произнося слово «солнце», что само по себе очень важно, потому что позволяет обращаться к нашей базе знаний через языковые идентификаторы, то есть вторая сигнальная система, а не демонстрируя реальные объекты, которые могут быть недоступны. Значит, вот разработана технология, как звуковые сигналы преобразовать в бинарный вид, в виде, значит, вид такой поступающей последовательности нервных импульсов. Технология, как выращивать, создавать нейросеть, которая будет соответствовать этим часто повторяемым звуковым словам. И, значит, эта сеть будет ассоциировать, значит, реальные объекты с звуковыми идентификаторами. Сеть выращивается уже как бы в постнатальный период у ребенка, когда он обучается словам, и дальше происходит обучение. Поэтому очень важно как бы обучать языку в определенном возрасте, пока еще нейросеть растет у человечка. Значит, к чему это приводит? Это приводит, ну вот самые какие-то элементарные, значит, ситуации. Например, когда робот распознает какую-то, скажем, ситуацию, скажем, некое препятствие. Если в это время вы будете несколько раз произносить какой-то звуковой идентификатор, скажем, говорить, что препятствие справа, в конце концов, где-то в нейросети это ассоциируется, и дальше вы можете просто роботу говорить, скажем, препятствие справа, и робот будет поворачивать налево, потому что он, для него это ассоциированные вещи. Это самое простое как бы применение. Значит, вот просто пример практического применения. Там погоня двух коптеров друг за другом. Вот, и, значит, оператор, мало того, что коптер научился, значит, догонять вот, ведущего коптера, но еще и оператор, значит, говорил ситуации, когда слева, когда справа ведущий. И в конце концов, значит, коптер задний обучается, и можно, скажем, в тумане или при потере цели подсказывать коптеру, где находится ведущий коптер. Но качество управления при этом возрастает. Значит, вторая вот ошибка, на которую я хотел бы быстренько указать, это то, что до сих пор, значит, почему-то такое бытует убеждение, что система управления должна моделировать совокупность рефлексов. Это, мне кажется, глубочайшим заблуждением, потому что рефлекс – это, извините, очень простая вещь. В механике это некий рычаг, в биологии это, извините, там рефлекторная дуга. Вот. В математике это не что иное, как просто функция, да, где как бы аргумент переходит в некоторые значения функций. В этом нет ничего хитрого. И я вас убеждаю, что искусственный интеллект на совокупности рефлексов построить невозможно. Это нечто совершенно другое. Поэтому я предлагаю вот от формулы рефлекса перейти к некоторой более сложной формуле. И попутно вот говорю, что все методы, которые используются в управлении, они по сути своей реализуют рефлексы по формуле стимул-реакция. Значит, предлагается другая схема. То есть от рефлекса надо переходить вот к схеме управления, основанной на знаниях. То есть система управления при распознавании данной ситуации не рефлекторно должна выполнять что-то, что ей там навязал учитель. Она должна покопаться в своей базе знаний, найти там варианты своего поведения, которые изложены, записаны вот в такой форме, пояснять некогда. То есть здесь нарисована формула причинно-следственных связей между ситуацией, действием, результатом в виде ситуации и эмоциональной оценкой, качественной оценкой. И вот каждый раз система управления выбирает лучшую из них. Значит, эти знания берутся эмпирически на основе анализа ситуации в прошлом, во все моменты времени с минусом, а экстраполируются на будущее именно в силу выполнения статистического критерия. То есть раз выполнялось в прошлом, будет выполняться и в будущем. И поэтому вся система управления – это не просто ИНС, нейросеть, это только вот этот блок в общей схеме системы управления, соответственной в мозге. То есть мозг, помимо распознавания, еще массу всего выполняет всяких действий, которые почему-то не учитывают при построении системы управления. Можно, конечно, все это выбросить и закоротить распознавание образов сразу на актуаторы, если вы знаете, что делать с тем или иным результатом распознавания. Но это не есть правильно, потому что человек сначала распознает образы, а потом ищет способы, как с ними бороться. Да, как бороться с этой болезнью или с этим объектом и так далее. Так. Значит, формула управления, которая была там написана. Вот если ее снабдить вот этими самыми средствами образования языковых идентификаторов, да, все, закругляю, то можно сформировать язык. Спасибо, собственно говоря, все. Вот здесь написаны возможности, как использовать язык в жизни. Благодарю вас.
Okay, yeah, I'm sorry we didn't have, synchronous translation, but, what we heard from Alexander Arkadyevich is really transition from radio technology And by the way, I'm pretty sure that some of your articles of Alexander Arkadyevich have been translated. It's really very exciting concept, what you said. Practically, this concept really is a concept of hierarchical structure of the brain. It's a structure when, each, just part of the brain works like the whole brain, but in some particular, just particular area, and has opportunity to process, to do, some analysis, to, construct a picture and make some, generate some decisions. It's really very exciting and interesting. And hopefully we will see justification of the thing and particular applications in technical systems, because we know just a lot about guidance and control systems where just exactly they're designed on reflectory type of thing, reacting to reflectory type of thing on external impact, but smart systems have the future. Okay, thank you very much. We have very short time to schedule time to our lunch break. So this is my report. I will try to be really very brief. I hope that we will have opportunity during our breaks and so maybe to discuss if it is of particular interest. And please go forward with my report. I will go through quickly. Where is the clicker? Okay, thank you. My report really a continuation of cyber, just topic of our conference. Cyber is, you can see below my title as a professor, I am head of Laboratory of Cyber Physical Systems at the Skolkovo Institute of Science and Technologies. And my report title is Digital Design Technologies in the Development of Complex Aerospace Products. What we were talking about, you know, for example, from radio technology is all kind of, you know, issues on propagation of waves, of, you know, just use of optimal use of spectrum and this kind of thing. But you can do nothing without real physical units, without receivers, without transmitters, without all these kind of things. You know, you need to have something material to support all these activities. And this is what I will be talking about. My background, I graduated from Moscow Institute of Physics and Technologies in 1972, you know, a long time ago. I had a pretty long career in former Soviet Union, and after that I had about quarter-of-century career in the United States, a bit more. Most of my career in the United States, I was working for a major defense and aerospace company. It is Orbital ATK. We were making, and the company continued to make rockets, satellites, and all these kind of things. So, and I was there from the very beginning, and I joined this company in '95 at the mid to senior level management positions, responsible for development of some new technologies. And so 2 years ago, I came back to Russia. I retired from this company, you know, in 2016, came back to Russia. Had offer from Skolkovo Institute of Science and Technologies, really from MIT. I had so very long, you know, relationships with MIT, and they offered me to come to support establishment of this laboratory, what I have done here. This is my fourth participation in this conference. I missed only one, and this, so just in previous my reports, I presented how things were working and how things were done in the United States in my previous company, ATK. And now I will try to present to you what we have done here, you know, for these 2 years, okay? And so, first of all, laboratory is cyber physical systems. Okay, of course, because it's cyber physical systems, first letter is cyber. It means that we are doing a lot with digital technologies. And digital technologies are, you know, everybody talking about digital technologies, information technology, and so on. But leverage and so comprehensive and productive use of digital technologies is something what really make a difference between death or prosperity of particular companies. You can see here on this chart that, for example, from year 2000 until 2017, about 50%, half of big companies which were part of the Fortune 500, they disappeared. Okay, everybody know, for example, story of Kodak, of you know, troubles with General Motors, with all this kind of things. Companies disappearing mostly because they do not understand how to behave, how to live in new environment. They do not leverage, they do not use what are the best things were developed by science and in management and control, in development of new technologies. There are a lot of really discussion, so just talks and thoughts about what is the critical success factor, for example, in introduction of digital technologies. And I would say, you know, in my experience in the United States, there is the most important criteria. How fast you can deliver to the market the new product, which is better than competition, cheaper than competition, and supported better than competition. The rest doesn't matter too much. The rest, all other things are derivatives. So you need to make better product, faster, deliver it to the market with the right price. This is what is this about. And during the next 10 years, 40% more of you know, big Fortune 500 kind of companies will disappear because they're behind. They do not know how to use this, what digital age bring to the market and to development of new systems. But digital technologies introduction needs to, for example, here in Russia, I hear from time to time that digital age is when you introduce and use a huge number of different technologies, software, systems, and so on. It's complete nonsense, okay? Because this is a great scientist, economist, Robert Solow. He is, by the way, MIT professor in economics. And you see, in '87, he said, you can see the computer age everywhere, but in productivity statistics, you cannot see any result. You can see here in this chart that until about '95, there is no return on investment. People were so playing with computers, they were doing all kind of interesting things. So just play music, all this kind of thing, but there was no return on investment. There was nothing, no impact to the economy. Why? What do you think? Why? And the reason is what was mentioned in your report, Mr. Wang. It is because there were, so of course internet wasn't invented before that, before '95. But I remember very well what was in internet use in '95, before the '95. It was email exchange. It was very simple things when you just exchanged very simple pieces of information. There were no search engines like, Google, for example, or anything like that. Internet didn't become, a media for exchanging and generation of knowledge, of generation of kind of new media for creative use of these computers. And when all the computers became to be connected, when they started to be working in concert, when people started to exchange information between each other, generating new knowledge and new information, so that you can see explosive growth of return. Only in this situation, you can just expect growth and return on your investment in this digital technologies, information technology. Similar story, but this is everywhere. Similar story you can see in energy generation, for example. Prior to creation of, you see, this is electrical power lines. Electrical energy was not in use, was not needed. Electrical energy was, so just all phenomena were used like for scientists research this, what was this about. There were some tricks, circus tricks, how you can do some different tricks with electrical charges and so on. Only after you have network, when you have use of this energy spread across the territory. So, for example, this is for the United States. Territory of the states, you have explosive growth of both generation and the use of this energy. Similar story is with cars. You remember, of course, that Henry Ford established, mass production of cars. But cars were very inexpensive, but nobody needed it because there were no roads. Roads in the United States, roads, were created in a network of highways after World War II. And after that, you can see, again, explosive growth of these things, okay? Okay. I was working, as I said, in an aerospace defense company, and our major customer was NASA. And NASA, very early in the history, understood that this is a core. This is something what needs to be developed and leveraged for NASA interest. And there was a great mind and a great NASA administrator, Dan Golden, who came out with this idea. It is NASA Intelligent Synthesis Environment. And the idea was really to create some environment with a digital environment, which was accessible for any contractor, for any, just NASA lab and so on, to make sure that you can integrate all the knowledge within NASA community and leverage this knowledge and develop new products on the basis of, like Isaac Newton said, we are great because we are stepping on the shoulders of giants. So this was the idea. And this is what is the result of this work, NASA work. It is by 2017. NASA really offers to all the contractors, to all the people who work for NASA, a huge library of all kind of computer, IT systems of this information and so on. Of course, it is mostly restricted to domestic US customers. You have a lot of restrictions for foreigners, for example, and so on. But we really were using this widely. But of course, I mean, mostly this is a just supporting type of software and systems. And so like reference type and so on, but it is extremely, extremely useful. In my company, what I was working for 20-something years, Orbital ATK, in addition to NASA, this environment, NASA systems, we of course developed our own, network of software and so on. It was based on Siemens PLM Team Center. You see a lot of software items which supported our development of new products. And I do not have time to elaborate on this thing, but believe me, every motor, every system what ATK was developed and released was different to the previous one. There were no two identical systems. It's always learning process, it's always development of new products, how this works. And because of that, you can see that the development is a not linear process, it's a cycle. You never get out of this cycle. You continue going on and on and on. It is like a spiral going up, it's on and up. So how this works? And it must work this way. Otherwise, you are dead, okay? So just one example from ATK experience. On this, I will finish on ATK experience. Just one example. In the beginning of 21st century, there was project, NASA project for development of new launch vehicle. It's called Ares. And development of this new launch vehicle, of course, on the basis of previous technologies, took 12,500 work weeks of our scientists and engineers. In about year 2010, this program was shut down, and instead there was a challenge from NASA to develop very quickly, instead of this rocket, two boosters about the same size. Rocket people, they know that boosters and the rockets are completely different animals, okay? Because of structural, all this kind of things, they're completely different things. But using this knowledge and the technologies developed, our scientists, engineers used only 120 work weeks to complete this design to the same level, okay? So you can easily, compare these things, and productivity was 2 orders of magnitude. This is what was the gain of productivity. And this is just normal result of comprehensive use of digital technologies and so just knowledge bases and all this kind of thing. This is one of projects what I was running for NASA. It is thermochemical regenerative energy storage system. This project was not too long. It was only one year. And it was within NASA Constellation program. We developed some energy storage system for lunar station. It was really pretty interesting stuff. This we got recognition from NASA. We got 2 patents on this particular technology. And now I will transition, 10 minutes. So I would like to say what we've done at Skoltech. You can see from the right-hand side a picture pretty similar to what I shown before. Under Team Center umbrella, we have a lot of software systems which are seamlessly integrated in our software environment. This environment, we really bought all this software. Everything is official. Everything is working, operational. We provide this media to our students, and these students, they do like miracles. So they develop very complex designs of very complex systems within a couple months. Our regular program of teaching, our teaching year is divided on 2 months, just portions. And you know, during these 2 months, our students need to develop detailed design of complex products. So everything is supported by this, you know, just environment of software systems and hardware. In the middle, you can see our equipment which works for justification of models. It's a physical, all kind of physical thing. And this is our class with first class, so hardware screens and so on and so forth. So our course of studies is organized around the famous V diagram, going from left and going to the bottom. This is a development of digital twin prototype of what you want to create. And going up, you have justification of model, finally getting to digital twin reference. It is, you know, just digital representation of a complete model of your system, the virtual model, along with the real stuff what you created. Okay? And I will give 2 examples of work of our students. One is a high altitude pseudo satellite. We were talking about, you know, in previous discussions about, for example, utilization of spectrum, of so efficient use of spectrum, this type of thing. And one of ideas, I mean, how to use this, how to create a system which would be the most efficient for spectrum use, was to, in addition to, you know, satellite and terrestrial system, to create intermediary, like, you know, this high altitude something, what can fly for long time, and they can which can retranslate. They can, you know, resolve issue of latency because they are not too high. You know, all these kind of things can be done with this type of unit. But problem is that this unit, this system needs to be in the air for a long time. Otherwise, it will up, down. It's from the point of view support of the system, it's very difficult. So, there is a very interesting phenomenon. If you see here, you know, at the altitude between 20 to 25 kilometers, there is no practically wind in the atmosphere. So if you put your just aircraft to this altitude, it can fly for a long time. And because you do not have any clouds or anything, you have always, you know, during daytime, you have always a source of energy. So you can fly there for a long time. But of course, during nighttime, you need to use some energy. So it is doable, it's a kind of feasible system, but it is tricky. But for example, here, this chart, very interesting chart. Using this only six of this pseudo-satellite, you can cover the whole British Isles with high, you know, just so with internet, you know, with very high throughput, very high, so 150 megabit per second, for example, it was 2001. Now, obviously, it is much more. So, and the question was, so it is known, you know, so known problem, and many companies and very many groups trying to develop these hubs, high altitude pseudo satellite. So this is what we gave our students. So this hubs needs to be able to fly from 2 to 6 months without landing at the 20 kilometers altitude using only solar energy with energy, you know, just collection system. I don't have time. There is some brief short, you know, video demonstrating one of these designs of this system, of these hubs. By the way, in China, there is such a project. You know, you of course, I mean, maybe remember. So there was recently launched one of in one of China universities. They launched this type of thing. Yesterday, I heard so Aviation Week and Space Technologies, Aurora. They put together this type of thing, but the world record in flight belonged to Airbus. They were in flight during about a month and a half. So all this, so if you compare these aircraft hubs, they are very different. They have different energy systems, they have different shapes and all this kind, the only common is, of course, they're huge. They're very big, they like from 50 meters, wingspan to like 60 meters wingspan, something like that, because they need solar panels, okay? And we tried to, not to develop the best, design of these hubs, but we wanted to try to, our students try to get them understanding why this or that particular design is doing this way, where critical success factors in particular technology, what technologies, is a bottleneck for, for implementation of these hubs and this type of thing. So we used, this is a great software from Siemens, it's AmiSim. AmiSim is a system which can, with which you can really put together very quickly model of any complex system what you want. And this model is just very easy not very easy. It is physical model, okay? It is model which really simulate all kind of physical interactions, so just information exchange and everything else in your complex system. But benefit of this model is that you can easily transition from this model, it is called 1D model. 1D because the only variable there is time, okay? You have dynamic model of functioning of the system. But using this library, which is incorporated in this AmiSim, you can easily transition into real three-dimensional model, what you can put together and will work, okay? And this is what our student did. So after they put together this model, they, did more in-depth analysis, all these kind of things, what are relevant to particular design of aircraft. Everything was done, you can see in the middle, it is optimization. Optimization was an inherent part of everything because at every stage, all the parameters, all the variables were optimized in accordance with some particular criteria. And this is, so just again, they developed model, okay? This model does not provide you final, the best in the world design, but it can answer what if questions. And this is only one example of this what if questions. For example, we just arrived to the idea, two designs of two motors hubs versus 4 motors hubs, okay? And both of them, they seem to be okay, okay? And so benefit of this approach is that all our models, including simulations and so visualization, are integrated in one environment, as I said. And you can easily do the answer to this question by simulation and visualization what will happen with these two versions of your aircraft. You can see next slide. So just to do that, we separated one of sub-models for flight. Our question was what was this difference will be in flight of these two versions of aircraft, okay? We separated model of flight and, analyze this model. And you can see here, this is from the left-hand side, it is 4-motor aircraft. From the right-hand side is 2-motor aircraft. You can see that from the left-hand side, it just went up and keep flying. And from the right-hand side, it doesn't have enough, power, thrust, and, it landed without, getting to the air. So it is the point is, again, you have the whole modeling system integrated, seamlessly integrated with one each other. You can easily understand what will happen, this and that. And I do not have time, of course, to elaborate on all the details. But for example, we found out that the most critical success factor for this thing is the capacity of the battery, particular energy density of the battery. And this is a very critical point. I do not have time to discuss it, but this was one of our results. So it is very rich environment. And again, what I said, our students did it for 2 months. For 2 months, this complex model. Just a second. Second, my example is very low Earth orbiting satellite. Very low Earth orbiting satellite is very similar two hubs, what I told before. It is satellite which can fly at the altitude between 150 to 150 kilometers. If you just launch satellite at this altitude, it will drop down to the Earth within a week, okay? But we want the satellite to fly for a long, long time. So, we tried to do similar things. So we developed model. We developed, quantitative, transition to this model. And as a result, with this model, we can analyze and understand which particular design will work and which will not work, okay? And for example, using this model, we evaluated this concept, which was offered by Busek, it's an American company. And using this model, we see that this particular concept will not work, because you see this is available thrust from this particular design with this characteristics, and this is drag. So in any case, this satellite will fall down. So we, using analysis, more in-depth analysis of particular technologies, we found out that critical point was collection of air, because this is just a propulsion here. Propulsion is based on plasma propulsion. It is energy is used from solar panels, and so just the working material is air, traces of air from outside, and that to make additional some reasonable thrust, you need to have more of this material. You need to collect more air during your flight, and the air there is very, very rare, of course. So you really need to get active air intake. And so we designed this active air intake, and as a result, you can see result that our thrust is higher than drag. So our design is supposed to be flying for a long, long time. So it is a kind of, at least, step to solution of a particular technical issue. So this is, by the way, evaluation of characteristics of this satellite. So it's supposed to fly optimal, is a flying of 235 kilometers, and the mass of this satellite will be about 200 kilograms. So this is what is it about. In a conclusion, I would like to say, again, both things were done during 2 months efforts of some small group, like 15 to 20 students. We divided between them particular tasks and assignments, and you can see that they do miracles. I was working with some former Soviet Union, design bureaus. For this type of things, they probably would use, like, I do not know, years of efforts. My conclusion is, so creating this environment, what I just said, creating these opportunities and seamlessly integrated system of software, you can really do many things, and you can solve the challenge to expedite development of new products to some levels of which were not imaginable before. Thank you. We are behind our schedule, but still, it's, I think, that 20 minutes. Okay. If you have any questions, we really don't have time right now, but I'm here until the end of the day. If you have any questions, please, I would welcome